Exercise related to stress strain and the Young's modulus. In this exercise, you will find the questions related to the topic stress strain and Young's modulus. I have already shared these assignments along with the answer key. So you can do practice. A motor uses a wire to raise a block as illustrated in figure 2.1. A motor is there. A wire positions are labeled X, Y, and Z. The weight of a block is 1.4 exponent 4 Newton and the figure is not to scale. The base of a block take about 0.49 seconds to move vertically from point X to Y. During this time, the wire has a strain of a 0.0012. The Young's modulus So the Young's modulus is 2.2 exponent 11 Pascal and has a uniform cross-sectional area. The block has a weight of 1.4 exponent 4. Assume that the weight of a wire is negligible. We need the cross-sectional area. So how we can work out the cross-sectional area? The Young's modulus is given. The strain is given. The force is given because the weight on the wire or the force is given. So we know the Young's modulus is a ratio between stress and strain. When we take a ratio between the stress and strain, we got the Young's modulus. So I can say that the Young's modulus is the ratio between the stress and the strain. What is stress? Stress is force over unit area. So I can substitute the values directly. So Young's modulus will be equals to F over A divided by strain. If I need the cross-sectional area, so A will be there in because this will be written like the Young's modulus is F divided by A and the strain. If I need A, so I just have to substitute the value force divided by the Young's modulus times the strain. So how much force is there? Force is the weight which is acting, and we ignore the weight of the wire. Otherwise, if let's say the wire weight was given to us, then we have to add that as well. But we ignore that, as in the question they mentioned that the weight of a wire is ignored. So the weight which is attached here is 1.4 exponent 4. The Young's modulus is given 2.2 into 10 to the power 11. Usually, remember, the Young's modulus is in gigapascal or megapascal, so it's a high value. Like if you get a number of a Young modulus in 1000 or 200 or 500, it means you are doing any mistake. And the strain is given, that is 0. The ratio between stress and change in length and original length is given. So when you substitute, we'll get the answer for this, which is 1.4 exponent 4, 5.3 exponent negative 5. Okay. And the unit is important. It's written here. So 5.3 into 10 to the power negative 5 meters square. That's the cross-sectional area. I have uploaded all the assignment and the answer key. In case if you don't find them, you can just let me know. I'll share again. But I have uploaded all of them. The questions, the assignments, the classified questions, as well as answer key. The increase in gravitational potential energy of a block from the movement from X to Y. So how much the gravitational potential energy has increased? It was moving at a constant speed and it took 0.45 seconds to reach from position X to position Y. So what we can do, if we need the increase in potential energy, gravitational potential energy, so it is mgh. And because it is about the change in increase, so it will be mg delta h, because we need the change. They mentioned it was moving at a constant speed So if something is moving at a constant speed, so we can work out how much distance it will cover from x to y. So from x to y, it was moving at a constant speed of 0.64. So 0.64 meter per second is the speed at which it is moving, and it took 0.49 seconds to reach there. So speed is distance divided by time. Why we did not use the equation of motion? Because the object is not accelerating. So for non-accelerated motion, speed is distance over time is a valid. So if I need the distance, it will be speed multiplied by time. The speed is 0.64 and the time it took 0.49 seconds. That will give us the distance which it will cover. That's equal to, the final answer is 4,300. Okay. But that distance is 0.316. Okay. If we need the potential energy, so the mass times the gravity, but mass times the gravity is also equals to weight. So I can directly substitute the weight here, which was 1.4 into 10 to the power 4, and the height which was 0.316. So we multiply, we'll get the gravitational potential energy, that is 4,390.4. So 4,390.4 joules. I'll use three significant figures. So I can write like 4.39 exponent 3 as I move 1, 2, 3. So 4.39 exponent 3 or 4.4 exponent 3 joules as a gravitational potential energy. Next, calculate the motor has an efficiency of 56%. So calculate the input power. So the efficiency is actually the useful energy divided by total energy into 100, or useful power divided by total power into 100. We have the useful energy, which is a gravitational potential energy. That is with
Oh
us.
my God.
We have the gravitational potential energy, which is a useful energy. The efficiency is 56. The useful energy is how much? That we calculated last part, 4.39 into 10 to the power 3. The input energy is unknown into 100. So if we need x, so it will be 4.39 into 10 to the power 3 times 100 divided by 56. But that will give us the energy because we substituted the energy, but we need the power. So how to work out the power? Power is energy divided rate of doing work, or energy divided by time. So after working out the energy, what is this answer for the input energy? 4.39 exponent 3 times 100 divided by 56. What's the answer for this? 7,839 joules. Okay. So we got this answer in joules, but we need the power. So we have to divide energy divided by time, will get the power. What was the time in the question? It was taking 0.49 seconds to read there. So we divide by 0.49. So 16,000 watts. Okay. 15,999 watts, or 16,000, or you can also say 1.59 exponent 4. So that is the input power. The base of a block now has a uniform deceleration of 1.3 meter per second square from a level y to until it stop at z. Calculate the tension from y to z. So if we need a tension here, the block is decelerating. So if the block is the tension is always to direction of a tension is to pull, and the weight is acting downward, and it has an deceleration of, what is the deceleration given? It has a deceleration of 1.3. So 1.3 is there, meter per second square. We need the tension. So according to Newton's second law, the resultant force will be equals to ma. What about the resultant force? In this case, the resultant force will be T minus W, but because it is decelerating, as it is decelerating, so which force should be greater? The W should be greater. Because if it was accelerating, then I should write T minus W. But in this case, I should write W minus T. So W minus T is equals to ma. If I need T, can we just take a negative? Yes, that's also fine. You can just take a negative value directly and you will get the same result. It does not make difference. You can, in that case, you can say T minus W is equals to minus ma. So it's fine, the same thing. So W minus ma will be equals to T. So W is a weight. Which we have already 1.4 into 10 to the power 4 was there. Minus the mass. What will the mass? It will be weight divided by gravity. So 1.4 into 10 to the power 4 divided by 9.8. This will be the mass. And what about the acceleration? Acceleration is 1.3. The deceleration is 1.3. So this will give us the value for T. So this is the mass. This is an acceleration, a deceleration, I mean, and this one is a weight. 1.2 exponent 4. So the tension will be 1.2 into 10 to the power 4 Newton. That's the tension in the string. So first it was moving at a constant speed and then it is decelerating. Sketch. Yeah, 1.59. Check again with these results. The weight 1.4 exponent 4 divided by 9.8 times 1.3 and subtract from the weight. One point two exponent 4, okay. The base of a block is at a level at x, y, and z in terms of tx, ty, and tz. On a figure, sketch the graph to show a variation with the time, the distance d of a base as level from x and numerical value of a d. And so this is the distance time graph. Distance time graph, what the slope represent? The slope represent the speed. So first from x to y, it is moving at a constant speed. And from y to z, it is decelerating. And the distance of x to y is greater as compared to distance from y to z. So we want to show that how we can represent. So from x to y, what we should do? We should draw a straight line. You can annotate on the screen if anyone want to. Because from x to y, it is accelerating. Sorry, not accelerating. I mean the constant speed, yes. And then from z, it is stopped, but it shows if you draw like this, it means it has stopped here, like before that. At z, it has stopped. So the graph should be more precise. And the distance also, like comparative distance. At this point, it has stopped. Another question related to the stress strain. A uniform metal bar initially unstretched has a size of length WXY as shown in the figure 3.1. How we know it is a stop? Because in the question they mentioned that. In the question, it was mentioned that it was stopped at Z. I read somewhere here. The block stopped at level Z. That's why. So we applied a force and we observe the new lengths are Z, X, Y, Z. And that means the length has changed. That's why Z is used. Determine the expression in terms of or sum or all FW XYZ for stress, strain, and the Young's modulus. So if I need a stress, what should be the expression for a stress? Stress is force acting on unit area. So if I need a stress, the force. What about the area I should take, the cross-sectional area in this case? Because we take the cross-sectional area. So what area is here? So X and Y, the product of X and Y will be the area, or Y and X, you can also say. Same thing. So I'll take this area. So it will be X times Y. If I need the strain, it's a change in length. Originally it was W and now it is Z. How much the length has changed? So Z minus W divided by W. The change in length divided by original length, that will give us the strain. And the Young's modulus is the ratio between stress and strain. So we have stress and strain. So stress is force xy divided by change in length over original length. So when we simplify this, it will turn out to be f w divide xy will go there in division. So xy times z minus w. That will be this Young's modulus, because Young's modulus is stress over strain. So next we have a copper wire is stretched by a tensile force. So when we apply a force to increase the length, we call tensile force, and it increases from 0 to 280 newtons. The variation of extension for a tensile force is shown. State the maximum extension of wire for which it obeys the Hooke's law. Hooke's law means it should be a straight line. For a Hooke's law region, it must be a straight line. So till which point it is a straight line? So we'll use a ruler scale and we work out the length here. So the last point it appeared to be straight. So this is a point where it appeared to be straight. And it will have a range in exam. These type of questions usually have a range. It's not like exact answer. So what is the length in millimeter? It looks like 2.10 boxes equals to 2. So each is 0.2. So this is 2.2, 2.4. It looks like 2.4. 2.4. The 2.4 millimeter is the extension. Use figure 3.3, determine the strain energy at the force of 120. So if the force is 120, first we'll mark when the force is 10 boxes equals to 80. So each is representing 8. So this will be 88, 96, 104, and 112. And this looks 120. So this is 120. So area under the graph we'll take, it will be half base into height. So what is the base here? So 10, 1, 2, 3, 4, 5, 6, 7 boxes are. So it means it is uh, each is 0.2. So 7 boxes, 1.2, 1.46. No. It will be 0.2, 4, 6, 8, 1.0, 1.2, 1.4. Sorry, 1.4. The base is 1.4 millimeter, but I'll convert into meter. So it will be 1.4 into 10 to the power minus 3 meter. And the height is 120. So I'll use a formula half base into height. So 1.4 into 10 to the power 3 times the force times 120. We'll get the energy here. That will be in joules, which is 0.084. Okay. So 0.084 joules is the energy. The next is explain why the work done in stretching the wire to extension 12 millimeter is not equal to energy recovered when the tensile force is removed. Like when we extend to 12, so what might happen? The spring might deform come permanently, or even if it is not deformed permanently, but what will happen? Some of the energy always stored or remain in the spring as an internal energy. So when we do a work done on the spring and work done by the spring, they're not same. Why? Because some of the energy, like some of the energy when we did a work done, that is causing a deformation of the spring. So it remain as a internal energy. So we can say the spring may deform, either you can say a plastic or elastic deformation happen. And the second point you will include that the energy dissipated or energy stored or energy loss, you can also say, in the form of heat energy. So this is about the stress strain and the Young's modulus questions. Next session we'll do more from different